So let's look at a few out of 7.1 through 7.3. So there's an identity sheet under modules in Canvas, and we're going to be using that identity sheet a fair amount. So they want us to multiply this. So to multiply this, we would have to do sine alpha minus cosine alpha times sine alpha minus cosine alpha. Remember, when we have things subtracted, we can't just square each one. There is a shortcut to squaring that out, or we could just FOIL it out. So distribute the sine. So sine times sine is sine squared. Then sine times cosine. And then distribute the cosine. So negative times positive. Since we called this one sine times cosine, when we multiply those, let's call that sine times cosine. And then when we multiply here, we get cosine squared. So we have these two are alike, so we can combine those. Minus one of those, minus another one of those, that's minus 2. Already got a minus. Minus 2 sine alpha cosine alpha plus cosine squared alpha. Now, one of the identities in 7.1 is that sine squared plus cosine squared equals 1. And that's true regardless of what the angle is, as long as the angle is the same for the sine and the cosine. So we have sine of an angle squared, cosine of an angle squared, and sine squared doesn't mean the angle is squared, but it means we have sine times itself. So whatever we get for sine, and the same thing for cosine squared. Cosine squared means cosine times cosine. So if we have a sine squared plus a cosine squared, we can rearrange this. Sine squared plus cosine squared, according to this identity, is the same thing as 1. And then we have minus 2 sine alpha cosine alpha. For 7.1, it will probably let us leave it that way. These are not like terms, so we can't do 1 minus 2. The 2 goes with the sine alpha cosine alpha. Now, in the next section, we're going to find out that when we have twice sine times cosine, these angles being the same, that's equivalent to sine of twice the angle. So if we know sine of one angle, cosine of that same angle, if we multiply those together and double it, that's the same answer we would get if we double the angle first before we take sine of it. And the benefit of that is that we can simplify that expression to something simpler. So 2 times sine times cosine is sine of 2x. Not sine squared. We're not squaring anything here. We're just doubling that angle, and then we're taking sine of it. All right, the next problem asks us to factor, and then if it will simplify, to simplify it. So while this is not a quadratic equation, plus that same thing that's being squared to the first power, and then minus 10. So imagine instead of having cosine x, we just had x. Cosine x all squared in the same place. So if this is what we had, we would factor it times x. We would have a 10 and a 1. and to get the 10 to be negative and to get a positive 1 there, let's see, we would want a positive and a negative like that. Now it might take you a little while to get that correct combination, but notice our inside product is 10x, our outside product is minus 9x. 10 minus 9 will give us the 1x in the middle. So that's how we would factor if we had a quadratic. This has the form of a quadratic. It just, in place of our variable, we have the cosine instead. So to get 9 cosine squared, instead of having 9x, we'd have 9 cosine x, and cosine x here. Cosine, here it is, cosine times cosine. 9 is either 3 times 3 or 9 times 1. And to get the 10, we could either do 2 times 5 or 10 times 1. But as we saw over here, the combination that's going to give us the 10 here, the 1 here, is this one. Oops, I put that in the wrong place, didn't I? Is this one. Notice 9 cosine times cosine would be 9 cosine squared. Cosine times cosine means cosine, or is cosine squared. Then we would have 9 cosine times minus 1. I still got a sign wrong. Okay. Got a plus here, so 10 times cosine would be 10 cosine. 10 times negative 1 would be minus 10. So we have our 9 cosine squared, we have our minus 10, and those would make 1 cosine in the middle. So yeah, that's how we would factor. So the same technique, we would use to factor quadratic. Just in place of our variable, we actually have a function instead. There's not an identity here, so there's nothing to simplify here. Same thing with this one. There's not an identity, so nothing to simplify there. All right. So the next thing they have us do is they give us the value of sine of one angle and sine of a different angle. They tell us that those angles are both in the first quadrant. They don't say in the first quadrant, but if they're between 0 and pi over 2, 0 is there, pi over 2 is there. So they're in the first quadrant. So they want us to find so we have an identity, and the identity looks like this. If we have sine of an angle plus or minus another angle, we can find that by taking sine of one angle, cosine of the other, and then cosine of the first angle, sine of the other one. Now, you might say plus or minus, what do you mean? We just have a minus here. This is actually two different identities. If we use the positive one, if it's an angle plus an angle, we use the top sign here. So we add them. If it's an angle minus an angle, we use the bottom sign here, so we subtract. So to calculate sine of this angle minus that angle, we would do sine of the first angle, cosine of the second angle. Since that's a minus, we put a minus here, and then we would do cosine of the first, sine of the second. So they give us a value for sine of both angles, sine alpha and sine beta. So in place of sine alpha, we could put 12 over 13. But we don't know cosine of beta. That's something we're going to have to find. We also don't know cosine of alpha. We do know sine of beta is 4/5. So the question is, if we know sine of an angle, how do we get cosine of the same angle? Well, there are several ways we can do that. So sine alpha is 12/13. and we're told we're in the first quadrant, we could just use the fact that in the first quadrant, or in general, sine is y over r. So if we randomly draw a terminal side, the y-coordinate of a point on that terminal side is 12. The radius is 13. So if we want to get x, we would just use the Pythagorean theorem. X squared plus y squared equals 13 squared. So x squared plus 144 equals 169. If we subtract 144 from both sides, we get 25. Square root of both sides. X could be plus or minus 5, but since it's in the first quadrant, we would do positive 5. This being angle alpha. So once we have the x, y, and r, then we could get any other trig ratio for that angle. So if we know sine of that angle, now we can get cosine of that angle. So cosine is x over r, so that's going to be cosine alpha. So we'll plug that in here. We need cosine beta, and we're told sine beta. We're told sine beta is 4/5. So we could do the triangle, or I'm going to do this one a different way just to show you a different technique. If we're looking for cosine, remember that sine squared plus cosine squared equals 1. So if we know sine is 4/5, we can substitute 4/5 in for sine. That squared plus cosine squared has to equal 1. So we can solve this to get cosine. If we square 4/5, 4 squared over 5 squared would give us this. We're going to have to take this away from both sides. So I'm going to go ahead and convert this 1 into 25ths. We need a common denominator. So 1 would be how many 25ths? 1 would be 25 25ths. So if we subtract 16 25ths from both sides, we get that cosine squared is 9 25ths. Square root of both sides. Cosine is, technically it's plus or minus, but since our angle beta is in the first quadrant, cosine is positive in the first quadrant, 3/5. Beta comes out to be 3/5. So that's just another approach. We could use x, y, and r, or we could use an identity. So we get that cosine beta is 3/5. So we multiply here, 12 times 3, that's 36 over 65. 5 times 4 is 20 over 65. So we get 16 over 65. So that's what we get for sine of alpha minus beta. Notice sine alpha minus beta is not simply sine alpha minus sine beta. It takes this whole identity to determine what sine of alpha minus beta is if we know something about alpha and something about beta. So all we did there is we used the identity. Here we're asked to simplify this one. So let's use an identity. For cosine alpha plus beta, the identity sheet is cosine of the first angle, cosine of the second angle. The identity has the same plus and minus deal, except with cosine, if there's a plus here, we use a minus here. So it's cosine of the first angle, cosine. sine of the first, sine of the second. So that's what we get for the first term. Then for the second term, it's cosine of the first angle, cosine of the second angle. If we have a minus here, we use a plus, sine alpha, cosine beta. Not cosine beta, sine beta. So these come straight from the identity sheet. So now if we look, we have some like terms. Cosine alpha, cosine beta, plus another cosine alpha beta. So that's 2 cosine alpha, cosine beta. And then these are alike. Except they're opposite. We have a minus 1 here, a plus 1 here. Minus 1 plus 1 cancels, so the sine alpha, sine betas cancel. There's not an identity here, so that's as far as we go with that one. All right. This one has us use some identities. So they give us cosine and they tell us it's quadrant. And then they want us to find sine, cosine, and tangent of twice that angle. Now, we could use a calculator to find theta, and then we could double that angle and take sine, cosine, and tangent of that angle. But that's going to be a decimal. If we take inverse cosine of 24 over 25, we're not going to get an exact angle there, which means any other calculations are going to only be approximate. Now, that would be perfectly fine to check our answer, but if we want to find the exact value, then we have to be a little bit more careful. Another thing they ask us for is the quadrant of 2 theta. So let's start with sine 2 theta. So how do we get sine 2 theta? Well, remember, we have an identity that we mentioned earlier. This is on the identity sheet. Sine of quadrant angle is the same as 2 times sine times cosine of just the angle without the times 2. So this is theta, this is 2 theta. So we have a coefficient and we know cosine theta. What we don't know is sine theta. But if we know that cosine theta is 24 over 25, then we can either use x, y, and r, or we can use an identity to find sine of theta. So I'm just going to use x, y, and r. We're told that theta is in the first quadrant. In terms of x, y, and r, cosine is x over r. So if we randomly draw a ray, then the x-coordinate of a point on that ray is 24 with a radius of 25. So over 24, we don't know how far up we are, but we have a radius of 25. And we can use the Pythagorean theorem to find y. So 24 squared plus y squared is the hypotenuse squared. So let's see, 24 squared is 576 plus y squared, I believe 25 squared is 625. So if we subtract 576 from both sides, we get 49. And if we take the square root of both sides, we get y is plus or minus 7, but we need a positive 7 here because we're in the first quadrant. So once we find this, then we know that sine is the y-coordinate over r. So if we know something about theta, then we can find out something about 2 theta. So we have 2 times sine, which is 7 over 25, times cosine, which is 24 over 25. This 2 as a fraction would be over 1 I do that just simply to help us see how to multiply this out. We do 2 times 7 times 24, which gives us 336 on top. And then we have 25 times 25 on bottom, which again is 625. Let me make sure I didn't type anything in wrong there. Yep. So this is sine of 2 theta. Then they ask us for cosine of 2 theta. Well, for cosine of 2 theta, we have three different identities, not two. We have cosine squared minus sine squared. We have 2 cosine squared minus 1, and we have 1 minus 2 sine squared. We can use either one of these, any of these we want. It doesn't matter. Now, often, if I'm given cosine of an angle, then I'll use the middle one, since cosine is what I'm given, and sine is something I had to calculate. But that doesn't really matter. Look at that. It would be twice cosine squared, and we were given that cosine is 24 over 25, so that squared minus 1. So that's 2 times 24 squared, which is still 576, over 25 squared, which is 625, minus 1. Since we're going to be subtracting these, we need a common denominator. So 1 we could call 625 over 625. Anything over itself makes 1, and we need a denominator of 625. So on top we have 2 times 576, which is 1,152. We're subtracting 625, and that's over 625. Our common denominator is 625. So we just took that minus that. So 1152 minus 625 is 527. And that's over 625. Is 527 over 625. For tangent of 2 theta. So we have an identity for tangent 2 theta, but if we know sine and cosine, remember that tangent, one of our identities for tangent is that tangent is sine over cosine. Thinking back to x, y, and r, on the unit circle, or even if it's not the unit circle, sine is y over r, cosine is x over r. Well, if we divide y over r by x over r, we would multiply by the reciprocal. So y over x, well, that's what we know tangent to be. So yes, this is a true statement. Tangent is sine of an angle over cosine of that same angle. So my point being that since we already know what sine is for 2 theta, and we now know cosine of 2 theta, there's no need to use double angle identity for tangent. We can just take 336 over 625, and we can divide it by cosine of that same angle. So we want to know tangent of the angle, take sine of 2 theta over cosine of 2 theta. So if we're dividing fractions, we're going to keep the first one, and then we're going to multiply by the reciprocal of the bottom one. So those cancel, giving us 336 over 527. So that's tangent 2 theta. 336 over 527. So this just goes back to our formula sheet, our identity sheet. The identity sheet is something you'll be able to use on your test I'm not going to make you memorize all of these identities or derive these identities. It is good to know where the identities come from. What's most important is that you know how to use them. So let's look at our signs, our SIGNS. When we calculated sine of 2 theta, we got an answer that's positive. When we calculated cosine of 2 theta, we got an answer that's positive. Likewise, for tangent, that was positive. So the last question is, what is the quadrant for 2 theta? So in which of these quadrants is 2 theta going to be in? Well, how can we figure that out if we don't know what 1 theta is? Well, we're told that sine is positive and cosine is positive. Remember, on our unit circle, the x-coordinate is cosine, the y-coordinate is sine. So in which quadrant is cosine positive and sine positive? Well, that would be the first quadrant. In the first quadrant, cosine, the x-coordinate is positive, and sine, the y-coordinate is positive as well. So 2 theta is in quadrant 1. Now, that's not something we could have just determined without doing these other calculations. You say, well, why not? Let's suppose that theta was 10 degrees. If theta is 10 degrees, then 2 theta would be 20. That is still in quadrant 1. But if theta is 50 degrees, then 2 theta would be 100 degrees. That's not in quadrant 1, that's in quadrant 2. So the quadrant for 2 theta is dependent on the angle of theta. Not just the quadrant of theta, but the angle of theta. Since we don't know the angle of theta, the signs, whether they're positive or negative, that'll help us know what quadrant we're going to be in for 2 theta. On this one, they want us to use a half angle identity to evaluate sine of 75. Now, we could type sine of 75 degrees in our calculator and it gives us an answer, but most likely it's not going to be an exact answer. So, using a half angle identity, sine of x over 2 is plus or minus the square root of 1 minus cosine x, all of that over 2. So the question is, how do we use a half angle identity to find this out? So in place of our 75 degrees, we have x over 2. If we double both sides, we would get that x is 150 degrees. In other words, 75 is half of 150. So sine of 150 over 2, using our identity, is plus or minus the square root of 1 minus cosine. So whatever angle we're taking half of, that's the angle we're taking cosine of. So 75 is half of 150. So we're taking cosine of 150 for this identity. Now, you might look at the plus and minus and scratch your head and say, how can sine be plus and minus? Or you might not have thought of that. Well, it can't. And at a single angle, sine is either positive or negative, or in some cases, 0. So the question is, well, which is it? Our angle is 75 degrees in the first quadrant. Well, in the first quadrant, everything is positive. So when we come up with an answer for this, sine is going to be positive. So we're not going to use the negative, even though our identity has a negative in there. This doesn't mean our answer is both positive and negative. It means sometimes it's positive, sometimes it's negative. That depends on where our x over 2 is located. In this case, 150 over 2, which is 75, that's located in the first quadrant. So we have to pick the appropriate sign for sign in the first quadrant, and that's positive. Now, what's the benefit of this identity to find out sign of 75? 75 is not one of our standard angles on the unit circle. In the unit circle, in the first quadrant, we have 30 degrees, 45, and 60, but we don't have a 75 as a standard angle there. But if we fill in for this identity, 150 is a standard angle. 150 degrees, is a standard angle in the second quadrant. It's this one. It's the one that has a reference of 30 degrees. Notice 150 is 30 degrees from horizontal. The point there is to the left, root 3 over 2, up 1/2. In the second quadrant, we're to the left and up, so negative and positive. Remember, on the unit circle, our ratios are 1/2, root 2 over 2, root 3 over 2. This angle is the one that's farthest to the left, so our x has to be the largest of those three, so root 3 over 2, and it's up the least, so the y value is the smallest of those, so 1/2. So sine of 150 over 2, or sine of 75 degrees, is plus the square root of 1 minus cosine of 150. At 150 degrees, cosine is minus root 3 over 2. Remember, on the unit circle, it's cosine and sine. So the x-coordinate, cosine. So cosine of 150, negative root 3 over 2. Notice we have a minus from our identity, and cosine is negative as well. So we end up on top with 1 plus root 3 over 2, all of that over 2. That's a complex fraction. We have a fraction that has a fraction in it. So to make our complex part go away, we need to make this denominator disappear. And recall the way we do that is we either keep, change, flip, or the opposite of dividing by 2 would be to multiply by 2. But if we multiply this term by 2, we have to multiply the whole numerator, and we also have to multiply the denominator by the same thing. So when we do that, we have 1 times 2 is 2. When we multiply here, this 2 and that 2 cancel, leaving us root 3. And on bottom, 2 times 2 is 4. When we have a fraction, we can take the square root of the top and the bottom separately. Well, the square root of the bottom is just 2. So the exact value for sine of 75 degrees can be written as the square root of 2 plus the square root of 3. All of that over 2. So recognizing that 75 is half of 150 and 150 is a standard angle, then we can use the half angle identity to find out an exact value of sine. When we use identities like this to find exact values, then we're going to be writing our angle in terms of standard angles of which we know the ratios. And those are going to be angles that are found on the unit circle. This one, they said use the half angle identity, so what angle is half of it is that makes 75. We could have used a sum and difference identity and rewritten 75 as 30 times 45. We have an identity that allows us to find sine of this. Remember, we have an angle plus an angle. We have an identity that lets us find what that comes out to be. based on 30 and 45. And the reason we use those is they are standard angles. So using standard angles to find exact values of non-standard angles. All right, here's another one that they ask us. They don't come out and say use a half angle identity. But if we're find sine of theta over 2, we know sine of theta, then the half angle identity says over 2 is plus or minus the square root of 1 minus cosine of theta all over 2. Now, from before, we said that it's not going to be both plus and minus. So which one is it? Well, if theta is in quadrant 1, so if our theta is in quadrant 1, that means theta is between 0 degrees and 90 degrees. Which leads us to know that half of that, theta over 2, is going to be between 0 degrees and 45 degrees. So if we know where theta is, then we also know which quadrant theta over 2 is in. Sine is positive in that region, so we're going to use the positive one, not the negative. Now, it would be nice if our identity was in terms of sine here instead of cosine, but it's not. If we want to know sine of half of an angle, we have to know cosine of that original angle. Well, we can find that. Remember plus cosine squared equals 1. So if we're wanting to find cosine and we know sine squared plus cosine, and I'm just going to write it this way as a reminder, cosine squared does add up to 1. So we can square this and move it to the other side. That will give us cosine theta squared equals, let's see, when we do 1 and we subtract 0.3057 squared, we get 0.9065 and some change. So take the square root of both sides. So cosine theta is, to 4 decimal places, that would be 0.9521. 0.9521. So that's cosine of theta. So we can get sine of theta over 2 by doing the square root of 1 minus, in place of cosine theta, put 0.9521, and then that goes over 2. So we can just plug that in our calculator. Do 1 minus that, 1 minus 0.9521. That answer gets divided by 2, and then we take the square root of that, to which we get 0.1548. 1548. So that would be sine of half of theta. All right, section 3 is probably one of the trickier sections, but it asks us to prove this identity. And when we prove an identity, we take either one side and try to rewrite it and make it look like the other, or we simplify both sides until we get to the point where both sides are exactly the same thing. But regardless, our goal is to make the two sides identical, to make them match. What we don't do is we don't move something from one side of the equation to the other. Now remember what an identity is. It's an equation that is true for all values in the domain. It's not just true for one or two answers. It's true for every possible angle there is. So when we prove an identity, we typically start with a more complicated side and we try to simplify it. So the left side seems to be more complicated. It has two terms instead of one. So the first thing I recognize is that they have a common factor of 8. So we can factor out an 8, and that's going to give us cosine to the fourth minus sine to the fourth. I also recognize that this is a difference of two squares. We can factor this as cosine squared minus sine squared, and we've got to make sure I put my angle in, times cosine squared plus sine squared. Just like if that was x to the fourth minus y to the fourth, we could call that x to the fourth is x squared times x squared, y to the fourth is y squared times y squared, and to get opposite signs, we'd have a minus and a plus. So we're doing the same thing here. To get a cosine to the fourth, we could do cosine squared and cosine squared, sine to the fourth, sine squared and sine squared, and opposite signs. So notice here, we have an identity. Sine squared plus cosine squared is 1. Also, if you look at your identity sheet, this is an identity. Cosine squared minus sine squared is cosine of twice that angle. So on the left, we simplify to an 8 out front, cosine of 2 theta times 1. Of course, we don't have to put that 1 because anything times 1 is itself. Notice that's exactly what we have on the other side. So if we can simplify one side and make it the same thing as the other, then we have proved that the two sides are identical. That for all values, they give you the same. All right, I think we have 2 more problems. So this one, they ask us to prove this identity. It's like the left side is the most complicated because we have 2 fractions. And when we have fractions that are subtracted or added, we often want to get a common denominator and combine those. So our common denominator is going to be cosecant minus 1 times cosecant. So this first fraction is going to be the pick up cosecant plus 1 on top and bottom. And the next fraction is going to need to pick up a cosecant minus 1 on top and bottom. Now both fractions have a cosecant x plus 1 and a cosecant x minus 1 on bottom. So they have the same denominator. Now if we were to distribute this out, you can do this on the side, cosecant here. We're going to have a cosecant x 2 different times, and we're going to have it 1 times 1. When we distribute this, we're going to have a cosecant times cosecant, so cosecant squared. We're going to have a minus cosecant twice, so minus 2 cosecant, and we're going to have a minus 1 times minus 1. So now that we've multiplied the top out and we have the same denominator, we can put these 2 together. So we're going to the first numerator and we're going to subtract the second numerator. We're subtracting all of that, so let's put the first numerator and the second numerator in parentheses so that we get our signs correct. That minus applies to that whole numerator. We're subtracting that whole thing. So we're going to subtract cosecant squared, we're going to subtract a negative 2 cosecant, and we're going to subtract a positive 1. Okay, so when we do that, cosecant squared minus cosecant squared would cancel. We have a 2 cosecant minus a negative 2 cosecant, so minus a negative would make that plus 2 cosecant. So 2 and 2, that would be 4 cosecant x. And then we have a 1 minus a 1. Well, 1 minus 1 is 0. Let's remind ourselves what the other side is. The other side is 4 tangent. 4 secant tangent. I have to be careful that we copy this correctly. It's cosecant plus 1, cosecant minus 1. So that's a minus. So I'm reminded that when I have factors like this, that's kind of what the difference of two squares looks like when it's factored. If we were to FOIL that out, we would have cosecant times cosecant, which is cosecant squared. We'd have a minus cosecant plus cosecant, which cancel, and we would have a minus 1. Now, when I look at that bottom and I look at the right, I notice the right doesn't have any terms. So I'm curious as to, is there an identity that we can take these two terms and convert them into one term? So one of our identities, one of our Pythagorean identities says 1 plus cotangent squared equals cosecant squared. Well, that does not look exactly like our denominator. But if we subtract 1 from both sides, that's okay because we're not proving this over here. This is an identity. We don't move things from one side to the other when we're proving an identity, but if something is an identity, we can rearrange it and it still be equal, as long as we use proper algebra. So cosecant squared minus 1, we could change that into cotangent squared. So the left is 4 cosecant x over cotangent squared. Now, I see some similarities, or at least one. I see that I have a 4 on both sides. So the question is going to be, how can I rewrite this to make it look like that? So there are different ways we could do this. One technique is to convert everything into sines and cosines. So on the right side, secant is the same thing as 1 over cosine. Tangent is the same thing as sine over cosine. So if we combine those, we have 4 times 1 times sine. And on bottom, we have cosine times cosine, or cosine squared. Okay, so on the left side, let's convert it into sines and cosines. So cosecant is 1 over sine. Cotangent is cosine over sine. Well, if it's cotangent squared, then we're going to square that. So we would square the sine and we would square the sine. So a couple ways we could keep a flip here. We have 4 times 1 over sine on top. And if we're dividing by a fraction, we multiply by the reciprocal. A sine on bottom will reduce a sine on top. So that's going to leave it 4 times 1 times sine on top. And on bottom, a cosine squared, which is the same thing we have on the other side. So yes, that is an identity. So that was harder than the other one. But the key is that we start added those fractions together to make it less complicated. Once we added them together, we continued to try to simplify that fraction as much as we could using identities. Once we got down to a point where it seemed like we were stuck, then we converted everything into sines and cosines. Once we simplified in terms of sines and cosines, we made the two sides match. All right, the last example is it asks us to take this and convert it into something using a sum product identity. So let me see if I can find those real quickly. Okay, so if we have sine of an angle minus sine of another angle, that's equivalent to 2 times cosine of the angles added together over 2 times sine of the angles subtracted over 2. When we subtract, notice it's the first angle minus the second angle here. So if we use our identity, this would be in place of our x, this would be in place of our y. So it's not just sine minus 2 alpha. We don't simply angles. That doesn't work. So sine of 3 alpha minus sine of 5 alpha is 2 times cosine of the angles added together. 3 plus 5 would be 8 alpha over 2 times sine of the first angle minus the second. So 3 minus 5, that would be minus 2 alpha over 2. So that would give us 2 cosine 4 alpha times sine of minus alpha. I'd be fine with you leaving it like that. Or we have an identity for this, because often they like us to get rid of a negative sign in here. So if we have sine of the opposite of an angle, that's equivalent to the opposite of sine of the angle. It's not exactly just pulling the negative out front, but that's what it looks like. It's not going to work the same with cosines as it does with sines, but this is one of our identities. If we have sine negative an angle here, if we want to make that angle positive, we make it positive and we put a negative out front. So positive, positive, negative makes a negative. 2 cosine of 4 alpha sine of alpha.